All right, now we have number 40. We want to determine the concavity, intervals of concavity, and points of inflection. And remember that points of inflection is where the graph changes concavity. So if your concavity goes from either up to down or down to up, provided it's not at a discontinuity, of course, you have a point of inflection. There's no distinction like there is for relative min and relative max, where you have decreasing to increasing is one thing versus increasing to decreasing is the other. That's not the case here. Either way, there's no there's no point of inflection min or point of inflection max. So let's see. Okay, straightforward polynomial. No discontinuities. So you take the first derivative, 4x cubed minus 12x squared. Then we take the second derivative, which will be then 12x squared minus 24x. Set that equal to 0. So factor the 12x out, and if you set those equal to 0, 12x and x minus 2, you would get 0 and 2. So those are the values needed for the sign chart. So it breaks it up at 0 and 2. So our intervals go negative infinity to 0, 0 to 2, 2 to positive infinity. Pick our test values. Then we plug them into the second derivative. So I use negative 1 here. So you put in negative 1, you're going to get positive. Put in 1, you're going to get negative. Put in 3, you're going to get positive. Positive, negative, positive. So the intervals of concavity then would be concave up from negative infinity to 0, concave down 0 to 2, concavity up from 2 to infinity. Since we are changing concavity at both those values, those would both be points of inflection, 0 f of 0 and 2 f of 2. Of course, if you needed to know what the exact y value is, you would take 0 and 2 and plug them back into the original function right there. That's where you always get your y values from. So for example, I think you can see real easily if you put 0 in there, you're going to get a y value of 2. So had we needed to know the actual point on the graph, that's weird. Then we would have got 0, 2 would have been the actual y value. Let's see if I can plug the 2 in my head real quick. 16 minus 32 plus 2. Negative 6 would be negative 14. So the other point would have been 2, negative 14. Concave up or down. X to the 3/5, you're going to have all numbers defined. There's no discontinuities. So you take the first derivative, which will be 3/5 x to the negative 2/5. Then take the next derivative, which will give you, bring the negative 2/5 down, gives you negative 6 over 25 x to the negative 7/5. Now, just like the rule for critical numbers, if you have a value that makes your second derivative undefined, but yet it is defined in your original function, that goes on your sign chart. Now notice I'm not saying it's an inflection point yet, but it goes on your sign chart. Unlike the term critical number, that's always the case. A critical number may not always end up being a min or a max, but these values where you set the derivative, second derivative equal to 0, I think in my notes that I use wording such as possible inflection point or potential inflection point. They don't really have their own name, but you don't know if it's an inflection point until you check the concavity. But anyway, 0. 0 makes that second derivative undefined. So you set that equal to 0, you get nothing. Negative 6 equals 0, that's a contradiction. But right there, 0 makes the second derivative undefined, but it's defined in the original function. So I have 0 on my sign chart. Pick test values, plug them into the second derivative. I get positive whenever I'm on the left of 0, -1. Get negative whenever I'm greater than 0. So we have concavity up from negative infinity to 0. We're concave down from 0 to infinity. So we do have a point of inflection. Oh, I wasn't even asking for that, but yeah, okay. Anyway, well, we have that right. The concavity, and there would have that. So that would have turned out to be an inflection point because it did change concavity. This one, the algebra gets a little messy on this one. I'm hesitant to ask one that's this quite involved on the test, but let me run through it real quick. Yeah, it was a little much maybe. Product rule, derivative 2x is 2, and then here you bring the 3 down, change that to 2, derivative inside 1. And I factored out an x minus 4 squared from these two. So it left a 2 times x minus 4 to the first to make it third, and then plus 6x. And then, so there's my x minus 4 squared. And then I simplify the inside part, 8x minus 8. Plus, since we're dealing with points of inflection, we have to go straight to the second derivative here. Got to do another product rule. So I brought the 2 down, changed that to the first. F prime g, so there's your g. Over here you have f, and then your g prime would be 8. So the derivative of 8x minus 8. So once again, I factored out the smaller of the two. There was a 2 I factored out between the 2 and the 8. I could have factored out an 8 inside here, but by then now I've already done it, so that doesn't make that big of a deal. But the x minus 4, it does though. So I got it out in x minus 4, which means took it completely out. So all that was left here is, well, the 2 also, 2 and the x minus 4. So you're just left with the x minus 8 here. Over here, 2 times, I need a 4 there to produce that 8. But then I also need one more x minus 4 to make x minus 4 times x minus 4, the x minus 4 squared. So what did I do here? Tidied up the inside part of this. After, I might have factored out another 4 here, actually. Well, we can easily see. Wasn't necessary, but might be appears what it did. But let's see. If you combine all this, you have 12x, and then you have minus 24. So this part would be 12x minus 24, which means if you factor a 4 out of that and multiply it by this 2, that's what produces that 8 right there. But you could have done this without doing that, because you still could have taken, so sorry about the confusion there, but you still could have taken 12x minus 24. I don't know why I did that, since it didn't benefit anything. Because if you take 12x minus 24 and set that equal to 0, you're still going to get x equals 2. So it didn't really make things that much easier. Because when you set that equal to 0, and of course the 8 goes away because you divide by 8. So you just take each piece, set it equal to 0. X minus 4 gives you 4. 3x minus 6 gives you 2. So you have your two values will be 2 and 4 on your sign chart. So you kind of run through this process, pick your test numbers. It goes plus, minus, plus. So it goes up, down, up. Your concavity does. And then your inflection points, it's changing concavity at both places. And neither one, they're not discontinuities. That's important to note. So we have points of inflection at 2, f of 2, and 4, f of 4. All right. Another point of inflection, easy derivative, so I'll just kind of skip that. Set this equal to 0. The second derivative part equal to 0, you get 1. So there's only one number here that would have any effect on the concavity. It's x equals 1. So we go from negative infinity to 1, and then 1 to infinity. I use 0 as my test value. I use 2 here. You put 0 into the second derivative, that's clearly going to be negative. You put 2 in there, 12 minus 6, positive, negative, positive. So your first interval, negative infinity to 1, is concave down. 1 to infinity is concave up. And because it changes over there, without being a discontinuity, you have inflection point at 1, f of 1. Now, what do we have here? The second derivative test for critical numbers. This can sometimes be troubling for people to remember how it works. It's not hard to use it if you remember how it works. The second derivative test says that if you take your critical numbers and you plug, the critical numbers always come from the first derivative by rule. That's what, remember the second derivative numbers don't have any names. You take the critical numbers that came from the first derivative and you plug them into the second derivative and test them. And by definition, if you plug the critical number in and it gives you negative in the second derivative, that's a relative max. If it's positive, it's a relative min. If it's 0, it's inconclusive. It doesn't tell you anything special. Probably not either, but no guarantee. Now, let's see what we have. And in my notes, it shows why. That might seem contradictory logic there, that how it's a negative, and why would it be a max, and vice versa. Well, you can look at my notes to see it, but I'll sort of explain real quick. Is that if you were, let's say if you're take a parabola, an upward-facing parabola. If you're at that bottom point, the vertex of that parabola, you definitely have a relative min. But think about what the concavity of an upward-facing parabola is. It's positive, correct? So that means that point that's at the bottom of the vertex of the parabola is going to be in an interval that has positive concavity. So therefore, positive concavity does translate to a relative minimum, and vice versa. So you plug negative 1 into the second derivative, and you get negative 2, so that does make it a max. 0 is 0, which makes it inconclusive, and it probably wouldn't be either anyway. And then you plug the positive 1 into there, and you get positive, so it's relative min at 1, f of 1. So to answer this question, it's only asking relative max. So it would just be answer A. So only A is given the max. But, obviously we wanted to see the solution to all the possible scenarios. All right. Let's see what we have here. Number 45 is giving you information about a point and want to indicate what kind of point it would be based on that. So let's look and see what we have. Now the f prime of negative 2 is a 0. It guarantees you got a critical number. Now you can use the second derivative test here to indicate what that value is going to be. That'd probably be the easiest way to do it. Maybe you could sort of figure out a way to sketch it out or whatever, but notice that it's telling you that f prime, double prime, the second derivative at negative 2 is positive 3. So using that second derivative test again that we just did in the last problem, putting it's a critical number because it's showing you the derivative equals 0, into the second derivative yielding a positive value, that means relative minimum. So had it yielded a negative value, it would have been a relative max. So it is definitely a relative minimum. Okay. Come down here. What does this say? more f double prime of 4 equals 0. So now you're talking second derivative stuff. So that pretty much indicates, well, I think point of inflection is about the only answer this could be, but maybe this probably might have been better with another answer choice or something. Well, actually, though, it depends on the rest of this too, though. Because remember, it's only a point of inflection is if your concavity changes. So actually, if concavity is not changing. But really, though, for this to have a chance, if this is going to be 0, the first derivative would also need to equal 0, because then that would open up the possibilities of being, could it be a min or max, or could it be a point of inflection? It won't be both. Because if you take functions that produce same value equaling 0 in the first derivative and second derivative, it's not both. In fact, here's a good example. If you take y equals x cubed, the first derivative would be 3x squared. You get a critical number of 0. And then the next derivative would be 6x. So you would also get a second derivative number that would be 0. But there's no way it's both going to be a min or a max or an inflection point. In fact, what ends up happening is that, x cubed, and once again, it's going to look terrible. Well, actually, it doesn't have to look terrible if I just do this. Clear that out. I have no idea what this graph's set up to be scale-wise, so, that's good enough. Anyway, see, x cubed would not have produced a critical number at 0, because you're right here, and you do have a horizontal tangent there, but you would have had increase, so it would have been no relative extrema. But that would have been an inflection point, because you're concave down until you hit 0, and then you're concave up. But there's no way it can yield both, and so it is possible, for both the number that's entered into the first derivative equals 0 and 0 in the second derivative being 0, and then there's possible mystery of what it might be. This one really isn't. It's kind of a point of inflection, but so it's telling you the second derivative is less than 0 if x is less than 4, greater than 0 if it's greater than 4. Okay, that's kind of the only thing it could be here. Well, I guess that one really wasn't too exciting. It was kind of a sort of a giveaway there, I guess. But well, all right, that's okay. Looks like I even did a little sign chart here, didn't I? That was way more effort than needed, but that does match what I had, or even the little picture I drew right here, little chart, hand chart. But yeah, so it would have been a point of inflection. Well, yeah, this would have been too hard to actually write all this stuff out, but it won't be bad for me to say it verbally. So notice, in other words, it mentions, if you see the key on the sample exam I'm referring to. I just didn't feel like writing out all these. Oh. Yeah. Let's see what we have here. And we'll just kind of run through these. It wants to know at each of these points is the first derivative being positive, negative, or 0. And second derivative. Now, the first point, this sharp point, you would have the derivative, first and second derivative would be undefined. Or they're always it's undefined at the sharp point. But, like I said, they still would have been on your chart. You see, it's a relative maximum. It's not asking for that. You see it's a relative maximum, so it would have been in your first derivative sign chart. and it's kind of separating concavity. I know these are both concave up, but anything that sort of separates them you have to include. So, but the derivatives themselves would not have been any values. Let's come down here to B. B is going to have first derivative equals 0, but you're in a concave up interval right here, right? And so that means f double prime of B would be positive. I said, well, f prime of B equals 0. Let's look at C. F prime of C is positive because you'd have a horizontal tangent slope, positive, excuse me, not horizontal, pardon me, a positive tangent slope. So that means f prime of C is positive. That's actually an inflection point. So f double prime would have been 0 of C is 0. Inflection points can be hard to see a little bit, but if you look, you see that that's your positive concavity here, and then it's switching over to negative concavity. So f double prime would have been 0 of C is 0. Come up here to D. Well, I'm going to assume visually that f prime of D is 0. And then f double prime of D is also 0. That is like, you know what, that part of the graph, let's see if that confers that. Yeah, D there. This is what I was just explaining a minute ago about that x cubed graph. So at D, you've got y prime equals 0 and y double prime equals 0. Actually, from C to E there, it looks like the general shape of x cubed. What do we got at E? E has a positive tangent slope, so f prime of E would be positive. I think we're looking at another slight, it's another inflection point because the concavity is changing from up to down. So f prime of E would be positive. F double prime of E would be 0. Come to the top of F. We have a horizontal tangent line, so f prime of F, sounds weird saying that, f prime of F is 0, and we are right in the middle. F is right in a concave down interval, so f double prime of F would be a negative value. Come down here to G, negative tangent slope, so f prime of G would be negative, and then G is another inflection point, so f double prime of G would be 0, so you're changing one more time, concave down to concave up. Wow, okay, that was a lot to say there, so hopefully that helped clarify that up a little bit. .48. Yeah, this one's kind of a hard one to, I should have come up with one that has asymptotes in it, because if I do put this on a test, I like to use one with the asymptote. So this one's kind of weird, but so you can refer back to the notes on this stuff a little bit. But well, let's I don't know, this answer key is completely weird. I don't know what's going on here. I might have changed something in the problem. I don't know why that dash line's there, so please pay no attention to that. But I'll explain what I did here. Well, I like the asymptote, so check that out. Okay, f of 2 equals 3. That means for sure you got to have that point 2, comma 3 is on your graph. F double prime of 0 is positive when x is greater than 4. It's negative when it's less than 4. That means we're changing concavity. It's going from concave up to concave down. So you see this part of the graph. So actually, you got a little subject to interpretation. So I come down here, as long as I make it concave up. Now we don't know where that y value is at 4. So I just arbitrarily chose this location. So that's why a lot of times there's more than one correct answer. So it's kind of so notice it's concave up. As soon as it gets to x equals 4, no matter what the y value is, it's then changing to concave down. And there we go. So it's a concave up, concave down. Kind of boring, but hopefully you got the gist of that. I like it when it has also when it has some f prime information in there to help you see increasing, decreasing, and stuff like that, or f prime of like this one would have also had f prime of 4 equals 0, because this is one where f prime and f double prime of 4 would be 0. Yeah, we don't know where the y value is, but it certainly would have had a horizontal tangent there. Critical numbers, increasing, decreasing, concavity, points of inflection. Now, on exams, I generally don't ask for all of this done at one time. I believe this kind of comes from section 3.6 in the book, which is the summary of the graphing stuff. But, if you look at how it's all done for a problem, then you could be able to solve any little individual piece of it that you needed. Now, the first thing that comes to my attention here is that fractional exponent of 2/3. That's where we're going to have that weird definition of the critical number come in. No discontinuities. I would never ask a problem that has this fractional exponent and a discontinuity at the same time. Would never do that. That's way too much. Alrighty, so take the derivative. 2/3 times 3 is 2. Minus 2x. And now, see, look what I wrote to the right. Now, I didn't show this visually here, but if you drop that down, it would be 2 divided by x to the 1/3. So when you put 0 in there, that absolutely means your first derivative is undefined. A lot of times people will make the mistake and look at, 0 raised to anything is 0. Well, 0 raised to a negative exponent is not 0, because it's the same thing as dividing by 0 when you drop it down. So, okay. Actually, 0 to the 0 is not 0 either, but that's a different story for a different day. 0 raised to any positive number is always 0. So that's that weird definition there. Now, but we're still going to set this equal to 0 to look for any more possible critical numbers. That was just that part. So I factored out, this is a little tricky here. It might have been easier had I done this, now that I think about it, as kind of a cross multiply. Let me write that. Well, anyway, okay, I factored this out, and then I just kind of figured out by just simple addition here that, this had to be x to the 4/3, because if you just think about it, I had to, negative 1/3 plus what number had to equal that 1 right there for that exponent. And you can see if you multiply x to the negative 1/3 times x to the 4/3 and add those exponents together, you will get x to the first. I did it this way. Now this is going to look sloppy, but perhaps it would have looked better had I just moved the 2x over. That might have been a little easier. Drop this down. So if you move it, and that equals 2x. Well, I didn't visually, it's like I moved it over and then reversed them again. Then if you cross multiply, you get 2x to the 4/3 equals 2. Divide by 2. Oops. Yeah, that might have been a little easier to solve. Well, we just learned something here. Because look what happens then when I factored that out. That's exactly what I end up with, just a different way. You don't need that first part. That first part, because when you divide 2 over x to the 1/3 is not actually going to equal 0. Because remember, you'd only be solving for the numerator. But here, this part, so you end up exactly what I got right here. You'll end up set that equal to 0. That's x to the 4/3 equals 1. Now, one thing I didn't show here, these fractional exponents can be a little tricky. This actually has two answers, plus and minus 1. The way you would want to actually solve this, all right, let me erase this and start a new mess over here. I have x to the 4/3 equals 1. Now, it would seem logical to raise that to the 3/4 power, to kill the 4/3. That does seem logical, but it's not really correct because you would lose a solution here. So what you would want to do is the following. You would want to cube it, get rid of the bottom exponent first. Then you have x to the 4th equals 1. And then anytime you have x raised to a positive number equaling a positive number, it's always plus and minus. So, x to the same thing as x squared to the 1, x to the 4th to the 1. It's like if you had x to the 4th equals 16, x would equal plus and minus 2. So here's your plus and minus 1. I can see where that would be tricky because you're probably not used to working with positive exponents all that much. I'm sorry, fractional exponents all that much. Not positive, of course positive, but yeah, you see, it's because that because that numerator is positive. If the numerator would have been odd, it wouldn't have mattered. I mean, even. I'm sorry, not positive, even. Even, positive, and even, both. But odd and positive wouldn't have mattered. You would only got one answer. So it's that even exponent. So you have three critical numbers, 0, plus and minus 1. So before I do the second derivative, let me hop down here and let's look at our first derivative sign chart. So three separators on there, -1, 0, and +1. So we got 4 intervals. Pick your test points. Now up here, you see notice I labeled that this is f prime here. We do want the derivative here. And there are my 4 test values right there. And if you look at this, zoom in on this, you can see it goes positive, negative, positive, negative. So my sign chart then goes plus, minus, plus, minus. Of course, that means increase, decrease, increase, decrease. And increase to decrease will be a relative max at -1 f of -1. And like I keep saying, if you need the y value, you could plug -1 right back in the very beginning of this if you had to. Oh, don't want that. And you'll also have another relative max at 1 f of 1 because you have another increase to decrease. And then you have a decrease to increase right there in the middle. So you have a relative min there. Now let's look at the second derivative. So here was the first derivative. So -1/3 times 2 is -2/3. This one's actually going to be a little easier. -1/3 minus 1 is -4/3. So you have -2/3 x to the -4/3 minus 2. Now, once again, that drops down to the bottom. And you have this situation, I call it potential inflection point. Cut this off accidentally. We don't know yet if it'll be one. But it makes the second derivative undefined, yet it is defined in the original function. But if you take now this second derivative, like I've done here, and set it equal to 0, look what happens. Bring the 2 over, and then looks like I multiplied both sides by 3. I guess I could have got rid of the 2. Anyway, oh no, I multiplied the whole thing, I'm sorry. So you have 6x to the 4/3 equals -2. X to the 4/3, when you divide by 6, would be -1/3. Well, because of that exponent being even, that could never be negative. It would always, no matter what you put in there, would be positive. In fact, I'll show you in a calculator, but you have to use parentheses here to do it properly. Then you might think I'm wrong if you didn't do this right. But let's say if I put, I'll pick something that has an integer answer. Well, not an integer answer, I mean a non radical answer. -8 raised to, oh, actually, this version of the calculator does it lifts it for you. But if you were doing it just like a kind of a more normal TI-84, you would use the caret sign, the red sign right there, where it's red now, and then you would have to put 4/3 in parentheses. So this is probably a bad example here because it's already lifting it up for us. But you would absolutely have to have a positive number. Well, I could write it here. It would look sloppy, but it would get the point across. How to enter this in the calculator. You would have -8 caret and then parentheses around that right there. Very important that you have the parentheses around that. So the only thing that goes on our second derivative sign chart is 0. So there you go. So we put in 0 into your second derivative. Here's 0. You pick test points -1 and 1. They both produce in the second derivative. They both produce negative results. So you go, your concavity is down and down again. So the fact that it's the same means you didn't change concavity. Therefore, you have no inflection points whatsoever. And there we go. Guess you could take a look at the graph of this and see what it looked like. Could add that in there. Might have to do some weird stuff with the scale there, but let's see. 3x 2 divided by 3 this newer calculator really gives me trouble. Clear the whole thing. I find correcting mistakes more challenging. Minus 2x, what is it? X squared, excuse me. So we have minus x squared. Oh, that's my fault. But I may have to tighten this window down a little bit. Maybe not. Oh, well, that's not bad. That is actually not too bad. So you see we have increase, stops there, hits a relative max, decrease, hits a relative min, goes up again, increase, right there, to another max, then decrease from there. That matches that sign chart. No inflection points because that sharp point right there at 0, 0, you're just separating two downward. They're both, that's two separate concave down intervals, not one interval. So you see that's down to down. So, all right, that matches up pretty well. Now we're trying to find the same kind of stuff here. So we got a little quotient rule here. Hopefully it doesn't get too ugly. Okay, right off the bat, x minus 1 on the denominator, 1 is a discontinuity. So that means 1 goes on all sign charts, first and second derivative. It has to be included. It will not be a relative min or max. It's not a critical number. It's not a point of inflection. But it does separate your intervals of increasing and decreasing and separates your concavity. So it's very important that we include it as long as we don't use it as any of the answers, for extreme or points of inflection. All right, well, I'm going to skip the product rule here, quotient rule, so come down to the result of this. So here's your, just remember we only care about the numerator, so don't worry about the bottom. You set that numerator, that'd be real easy to factor an x out of there. So you would have x times x minus 2, so you would get 0 and 2 as your critical numbers. So I'll jump down here to the sign chart. So you see you have 0 and 2, and then you have 1 there. Once again, there's my dashed line for the discontinuity. But that does give us 4 intervals for increasing and decreasing. But keep in mind where that 1 is cannot be a min or max. So you pick your test points as usual, and then you plug this back into the first derivative. You see I have it right over here. It goes positive, negative, negative, positive. Right here, positive, negative, negative, positive. Increase, decrease, decrease, increase in those intervals. And then we would have a relative max at 0, f of 0, because we're going from increase to decrease at 0. Decrease to increase at 2 means a relative min. And then there we go for the first derivative. So let's come back and see what happened to the second derivative. Maybe a bit too involved, but it does simplify real nicely though. All right, quotient rule once again. Bottom times the derivative of the top, which is 2x minus 2. Top times the derivative of the bottom, which would be 2 times x minus 1 to the first, times 1. Derivative of the inside, chain rule, over the bottom squared, which will be to the fourth. So the quickest way to simplify this without factoring and canceling is find your smallest power, which is the first. Cancel that out, and then you reduce all the other ones by 1. So x squared goes to first, fourth goes to third. Or you can formally factor it out and cancel it. But we want to simplify that numerator if we can to make it a lot easier. So then you take 2x minus 2 and you FOIL it times x minus 1 to get this business. Now you got to be very careful here, because if you distribute 2 times x squared minus 2x, that does give you 2x squared minus 4x. But the outside negative will change both of those. So it becomes negative 2x squared and positive 4x. So actually, once you get past the derivative, this tidies up. Look at this. 2x squared is cancel. The 4x's cancel, and you're only left with 2. So you set 2 over x plus 1 cubed equal to 0. That's not going to produce anything. So we have no inflection points whatsoever. But however, though, so there's no inflection point, but that same discontinuity. See, critical numbers don't automatically travel from the first chart to the second chart. Some can, but that discontinuity has to go on that chart automatically. So you see, that's what's separating your second derivative. So even though there's no, potential points of inflection, that doesn't mean there's nothing going on there. So we separate it, so our interval goes from negative 1 infinity to 1, and then 1 to infinity, so we can answer the concavity part of this anyway. 0, test point 2, you get negative and positive, so you can say that you're concave down from negative infinity to 1, and you're concave up from 1 to infinity. And that's all you can really say. I don't know if I didn't graph this one, but I guess I could. Real quick. Make sure. X squared over x minus 1. Oh, not this mess again. Parentheses. right, let's see if we have to change the window. We may not need to. I think that'll be just fine. Let's see where I can put that in there. I'll put it right down there. Let's grab him and drop him right down in here. But notice on the second derivative, that's why you have to, that's sort of goes back why I use that dash line thing, is that's why I wrote this down here. It might be tempting to look at that. Oh, you see, it goes from down to up. So we are changing concavity, therefore it has to be an inflection point, but it's not. Nothing like that can happen at a discontinuity, and this is clearly a discontinuity. And, something's not right here. Put in, let me see what I put in the calculator. Let me double check what I did. Oh, wait a minute. Oh, yeah, that was I guess I didn't copy this properly. It just pasted that same graph from the last problem. No wonder I knew that didn't look right. Yeah, that can't be right. That's the same problem from one above. Get rid of that. Oh, wait a minute, that didn't match my concavity. So you see the concavity is clearly correct. Concave down, then concave up. And then we're going increasing, we're going up, down, down, up. Well, that matches this. Increase, decrease, decrease, increase. Got a relative max here at 0. We got a relative min right there at 2. Right there and right there. I think that looks pretty good. Critical numbers, all that kind of stuff. Same thing again. Polynomial, though, will be easy. The first derivative, 8x cubed, and then minus 16x. So factor out an 8 and an x, and you'll get 8x times x squared minus 2. All right, this one has a radical, but nobody will be harmed here. It'll be all right. So you've got 0, and then x squared equals 2. Don't forget that would be, remember, anytime x squared equals a positive number, it always has two answers, plus and minus 2. Now, obviously, there are other applications like, absolute extremum where you might throw an answer out. That doesn't happen here. Everything needs to be included. So very common. I'll see students, they'll mess up one of these things because they'll have x squared minus 4 and they only say 2. And that happens a lot. But this one's square root of 2, of course, but plus and minus root 2, so we got 3 critical numbers. So it looks scary, but it's not bad. So you just kind of fill that out and pick your test points, which I did here in blue. -2, -1, 1 and 2. negative, positive. You plug them, just plug those test values. Looks like I didn't put a calculator screen in there, but that's okay. Plug it right into that derivative or right down here, factored form, whatever you want to do. And you'll get minus, plus, minus, plus. So you have decrease, increase, decrease, increase. So it gives us two relative mins, because we have two separate and no discontinuities here. So decrease to increase and another decrease to increase. Then I have an increase, a decrease in the middle. So that's 0, f of 0. And that would be your relative max in the middle. So that takes care of the first derivative. Let's see what's going on with derivative number 2. 8x cubed minus 16x. The next derivative would be 24x squared minus 16. We're going to set that equal to 0. That's not too bad. Only the x squared. You'll end up with x squared equals 2/3. So just like the last problem, though, that yields two answers. It's plus and minus the square root of 2/3. So that's what will break up our sign chart on the second derivative. Right here. So you're going from negative infinity to negative root 2 over 3, negative root 2 over 3 to positive root 2 over 3, and then positive root 2 over 3 to infinity. Pick your test values. I used negative 2, 0, and 2. Could have used negative 1. Plug those in that second derivative. You'll get plus, minus, and plus. That means you have concave up, down, up. So therefore, there's no discontinuities here, so these points are all under consideration. So you have two inflection points, up to down and down to up. So it'd be negative square root of 2 over 3, and then f of that. Positive square root of 2 over 3, and f of that. Inflection points. So there we go. Let's see. Guess I could squeeze a picture of that in there real quick. May have to, although the window is going to get kind of weird, I have to adjust because the y values are going to get large in a hurry. 2x to the 4th minus 8x squared. Well, actually, they do get large in a hurry, but that's still enough to tell us what we need, so we don't have to down, up, down, up. We'll see if we can paste the correct graph in here this time. All right, where do I want it to go? Be the million-dollar question. Oh, right up there would be good. Alrighty, so that should satisfy my sign chart stuff. It's just some of the numbers are kind of weird, that's all. I mean, like this right here, that's negative square root of 2 for x, positive square root of 2, inflection point. I'm sorry, another, and then that's 0, 0. And then your inflection points, they're in here somewhere, right about there, where, it's hard to see them, but the concavity's got to be changing somewhere. So that's that negative square root of 2 over 3, whatever. So you see where I have it there. They're both numbers, the positive one's less than 1, and the other one's, they're between negative 1 and 1. So I might not have put them in the perfect spot there, but that basically gives the idea. Let's come down here. Number 52. Got a trig one, that's always fun. But this one I didn't get, I think it might have got too out of hand if I would have gone to the second derivative. So I didn't. Yeah, first derivative on this is enough. This will test your trig skills. A lot of people have a difficult time solving trig equations. Let's see. The derivative of 2 sine of x would be 2 cos of x. Now be real careful here because the chain rule comes into play. The derivative of sine of 2x is not just cosine of 2x. That's part of the answer. It's cosine of 2x, but it's then times the derivative of 2x. So you have to include that. So that's where that 2 is coming from, is the chain rule, the derivative of the 2x. So very important. Easy for people to forget that. So the derivative of sine of 2x is 2 cos of 2x. Now these would be on your trig sheet, these identities, but you need an identity to get rid of this cosine of 2x. And there's 2 other ways to write it. It's cos squared minus sine squared, and it's also 1 minus 2 sine squared. Now you're going to want either one of the ones that involves the 1. And to know which one to use, it all depends on what this other trig function is, if there is one there. If there is one there. Since this first part is a cosine, you want this to be only in terms of cosine of 2x, which leads us to that result. That's why we would pick that one. Because that way everything, it just turns into cosine. So I choose that. So let's see. I kind of got a little out of order here. Sorry about that. I kind of skipped a step. But anyway, I'll explain it. So if you take this 2 in front times this result right here, you're going to get 4 cos squared. I'll tell you why I did this in a minute. 4 cos squared, which is right there, and then 2 times negative 1. That 2 times this negative 1 makes that negative 2. Then I drop this down. I put this in sort of a quadratic function order because, believe it or not, it is possible to factor trig functions like you would quadratic. Now, first thing I did, which I would do with any quadratic equation, is reduce it if possible, because we're setting this equal to 0 to get the critical numbers. So it all divides by 2. Some people might look at this, third line and be kind of horrified about trying to factor that. But you know what you could do if you wanted to, just make it less scary to look at, is write it like another variable. Instead of cos squared, use it as y or something. I don't know. Then you're just dealing with this. Of course, you are going to have to change it. Oh, there should be a 2 there, excuse me. 2y squared plus y minus 1, and then factor it like this. And then it becomes 2y minus 1. So you see, it is like factoring a quadratic. Y plus 1. And then replace them with cosine. So your 2y minus 1 is now 2 cos x minus 1. And your y plus 1 is now cos x plus 1. So yeah, factoring quadratics. Looks pretty fun, doesn't it? All right, so I just actually skipped a step. I set m equal to 0, but that's easy enough. You set that equal to 0, you'll get cos of x equals 1/2. You set this one equal to 0, cos of x equals negative 1. So you can go to unit circle. We're staying between 0 and 2 pi, which I always do in these kind of problems. So you look at your unit circle, you would see that cosine equals 1/2 at pi over 3 and 5 pi over 3. And cosine will equal negative 1 at pi. So all those ones that are actually in your interval from 0 to 2 pi. So we have 3 critical numbers, pi over 3, pi, 5 pi over 3. So I come down to my sign chart. So I got them in there. See, pi over 3 is first, pi is second, 5 pi over 3 is third. And okay, I kind of mix it up here a little bit, but be careful if you do it the way I did this. I don't know why I did it. It's okay, but I just felt like using test values in degrees. But then if you do that, make sure that your calculator's in degree mode. That's very important. So if you look at that and go, I'm not going to do that, then that's fine. You want to just stick with radian and using, so like I could have just used pi over 6 here, which is what 30 degrees actually is, 2 pi over 3, and then just used radian mode. 240 is 4 pi over 3, and 330 is 11 pi over 6. I think. Yeah. So I don't know why I used degree, but obviously I would have made sure my calculator was in degree mode if I used degrees. But by all means, don't let that scare you. If you'd rather say, I'd rather use radians all the time, so go right ahead. So we have test values. I got positive, negative, negative, positive. So that gives me increase, decrease, decrease, increase. And so there I have a relative max at pi f of pi over 3 because it goes increase to decrease. Then I have a relative min at 5 pi over 3 because it goes decrease to increase. And nothing's happening in the middle because it stays decrease to decrease. So nothing happened there. So let's maybe take a quick peek at the picture of this, I guess. But now I gotta make sure I'm in radian mode. 2 cos x plus sine 2x. Wait, excuse me, 2 sine x plus sine 2x. Two sine x Alrighty, let's see. Mode. Radian, good. And my window doesn't really have to get too creative here. Actually, I'll show you what I like to do when I graph trig functions. You might find this helpful, but or not. Is I look at what my critical numbers are and I try to find a common denominator. Like if it was pi over 3 and pi over 6, I would use pi over 6. Whatever the put it in increments. So this one, they're both pi. They both involve some sort of pi over 3. And even pi is the same thing as 3 pi over 3. So in other words, the common denominator between 3, 1, and 1 is 3. So that's how I scale my axis is, and we only need 0, 2 pi. So I go 0, 2 pi, pi over 3. Don't need that much. It's not going to be that extreme between these two values. I'll just go negative 3 to 3. 1's okay for the y's, but I almost got a 3, didn't it? So I'm doing all the way to 0 to 2 pi. So we go copy that. And squeeze it right in there. And that matches the work that we did. Did that again. All right, shrink down a little more here. But now you can see that looks good because there's that flat spot in the middle, so that would have been increase, goes up. then down, decrease. There's still a critical number there at that flat spot, but it's neither max nor min. So technically it decreases, stops for a second, decreases again. And then we have another min down here. And there we go.